Hey everybody, you're watching What's Up with Giancarlo. So today we've got topic 7, lesson 4, compare theoretical and experimental probabilities. I can compare the experimental probability of an event in a repeated experiment to its theoretical probability. The standard for this is MA.7.DP.do.4. 2.4, excuse me. Use a simulation of a simple experiment to find experimental probabilities and compare them to theoretical probabilities. Ooh, sounds fun. Okay, let's move on. You guys can go ahead and take a look at this if you want. You just go ahead and pause your video, but I'm gonna move on. So we've got example 1. Find theoretical and experimental probability. So example 1 is Talia and Yoshi chose a spinner game for the school fair. They planned for 1 out of 8 or 12.5% of the players winning a prize. During the school fair, they kept track of the numbers of total players and winners and recorded the data. In the table below, how does the actual number of winners compare to the expected number of winners? Well, so they get 1 out of 8. You see a lot more than 8, right? So they get 1 out of 8 because there's 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There's 16 spots, but there's 2 win spots. Therefore, that is 2 over 16, and that simplifies to 1 over 8. So it is 1 out of 8, and if you do 1 divided by 8, that equals 0.125. And then as a percentage, you move the decimal over twice, or you multiply by 100, whichever one you want to do, you get 12.5%. Okay? So that is your percentage for that is your winning percentage, okay? So they say to compare the actual number of winners, which is right here. This is experimental data. They actually had people, real live people, spin, and they got winners, and they have the total players and everything, okay? So this is what we expect. So this is the winning percentage as a decimal. So to find out the expected number of winners, we take the total amount of players right here, 475, and then multiply it by the decimal, the expected winners decimal. Okay, so 0.125 times 475, and when you do that, you get 0.125 times 475. You get roughly, it's approximately, because I don't feel like writing out the whole thing, it is about 59.4, but you can't have 0.4 of a person, so we'd round that down to 59. Okay? So we had 59 expected winners and 58 real winners. Okay? So you can go ahead and pause if you need to write all this stuff down. I'm going to move to the next slide. Okay? So here it is. They show you step 1. You can find the experimental probability of everything. So this is the real percentage, winning percentage. The experimental winner percentage is 12.2, where our theoretical probability was 12.5. Okay? So that means we thought there would be more winners, okay? Which, when we compare the experimental probability of 58 winners to our 59 winners, this is theoretical, this is experimental. So this is experimental is after it's all worked out. Theoretical is before we actually do anything. This is what we think it's going to be with the probability of how things should work out. Okay, so this is how they work it out and everything. I showed you this on the last slide. So they say about 59 players were expected to win. We say about because it's still rounded. Okay, that's why they throw in about. All right. So the table shows that 58 winners out of 475 players. So the experimental was 58. That's how many actually won. The theoretical was 59. That's how many thought. That's how many we thought. So the experimental probability is pretty close to the theoretical probability of winning this game. There was only one fewer winner than expected. Okay, we expected 59. There were only 58. Pretty darn close. Am I right? I'm right. Okay, let's move on. Example one, try it. Okay, go ahead and pause. All right. During the second day of the school fair, Talia and Yoshi recorded 43 winners out of a total of 324 players. How does the actual number of winners compare to the expected number of winners? So, experimental probability, okay? There's supposed to be a line there that you probably don't see. Well, you'll see it on your paper. So 324 is the total players. That's why it goes on the bottom. So what goes on top? You're right. It's 43 winners. Good job. So we put 43 up here. Then we're going to work out the percentage. We're going to do 43 divided by 324. So what we get this long decimal. And then once we get this long decimal, we have to multiply it by 100, and that'll give me the percentage. Okay? So I get 13, I get 0.13271605. Does not matter. I care about the first four numbers after the decimal, okay? So I care about the 13 because that's the first two. And then the 27, that 2 is going to be my rounding spot. So the 7, I get 0.1327, blah, 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 blah. That's all I care about. So I move the decimal over, and then this 2 is going to either round up or down because of this. So 5 or more, let it soar. So that 2 is going to turn into a 3. Okay? So our percentage is 13.3%. Okay? So the experimental probability is greater than or less than the theoretical probability of 12.5%. Well, this is a bigger number, therefore it is greater, okay, than the theoretical probability of 12.5%. So there were more or less winners than expected. Well, we expected this amount of winners, we got this amount, okay? This percentage amount of winners, and we got this percentage amount of winners. Which one's bigger? The ones that we actually got. So there were more winners than expected. All right. Good job. Good job, everybody. Let's move on. Example 2, understand increased repetitions in experimental probability. Marcus rolls a die 3 times and it lands on an even number each time. He then increases the number of repetitions and records his results. What happens as the number of repetitions increase? Is the die fair? Well, we're rolling a number die that has the numbers 1, 2, 3, 4, 5, and 6. There are 3 even numbers and there are 3 odd numbers. So the chances of rolling an even number is 50%, and the chances of rolling an odd number is 50% in our theoretical probability. Okay? So if the die is fair, then after more repetitions, the experimental probability will better approximate the theoretical probability. So what they're saying is after we roll it more and more and more, the theoretical probability or the experimental probability after we roll it should be close to our theoretical probability of 50%. Okay, so now we see Marcus's table of rolling the die. So rolls it 3 times, rolls it 10 times, rolls it 20 times, rolls it 100 times, okay? Lands on an even 3 times, 7 times, 8 times, 48 times. It gives you all the percentages right here, okay? So after 100 times, landing on an even is about 48%. Now that's pretty dang close to our 50% for our theoretical probability, okay? That is pretty dang close. So as the number of repetitions increase, the experimental probability gets closer to our theoretical probability. Therefore, it is fair. So the die is fair. It is fair because it is very close to our experimental. The experimental probability is very close to our theoretical probability. Okay, it's pretty easy. Pretty easy. Okay, so let's look at this. Try it. Example two. Try it. Go ahead. Pause it. All right. Marcus rolls a die many times and records the number of times he rolls a six. Is the die fair? Okay, we're rolling a die. The numbers are 1, 2, 3, 4, 5, and 6. Okay, so he wants to roll a 6. That is one number out of 6 possible options. Okay, when you work it out, you get 0.166666. So we're going to round it and make it a percentage, which is roughly, sorry, I put the equal sign, it should be approximately or about 16.7%. Okay? So if we look at the number of trials, it keeps going up and up and up, okay? And then this is the amount of times he rolls a 6, and these are the experimental probability percentages, okay? Do you see any that are close to our 16.7% for a theoretical probability? You're right. No, not one close one. Therefore, this die is not fair. Not fair. Not fair. Okay, and we're done with this try. Let's go. Let's go. Yeah. Okay, let's move on. Example three. Example three. Explain differences between theoretical and experimental probability. Amir and Marvin each flip a coin 50 times and record the result of each flip. The tables show their results. This is Amir's results. This is Marvin's results. Okay, so if you flip a coin, there's only two options. Therefore, landing on one side would be 50%, landing on the other side is 50%. Correct? Correct. Let's go. Let's move on. Letter A. Based on theoretical probability, what are the expected results of 50 coin flips? Like I just said, there are two possible outcomes, heads or tails, and both outcomes are equally likely. So if you flip a coin, it's a 50-50 chance. So if we flip a coin 50 times, we should expect to get 25 heads and 25 tails after 50 flips. Okay, let's move on to letter B. Why might their results be different from the expected results based on theoretical probability? Hmm. Well, theoretical probability can be used to estimate results, but does not guarantee results. They are not guaranteed. It is just an estimate on what should happen. Anything is possible, class. Anything can happen. But the more times they flip their coins, the more likely it is that their results will be closer to the theoretical probability. Like we said in example two, the more repetitions and the more repetitions and the more repetitions and the more and more and more that we do, the more times we flip this coin, the closer it should get to that 50% of our theoretical probability. Does everybody understand? Good, get it, got it, great. Let's go to the try it. Example three, try it. Go ahead and pause. Okay, we're back. Amir and Marvin continue until they each flip a coin 200 times. How do you expect Amir's results and Marvin's results to compare? How will their results compare with expected results based on theoretical probability? So, we would expect Amir's results and Marvin's results to be close together, but not exactly the same. Okay, it would be it. It can happen that they can have the exact same results, but it's probably not going to happen. Okay, but they will be close. A and M results will be close together. Okay? How will their results compare with expected results based on theoretical probability? Their results will be their results will be close to the theoretical probability, but will not be exact. But oh no, oh no, oh no, oh no. But will not be exact. All right. And here's your key concept. There you go. Another lesson wrapped up perfectly. Thank you everybody for tuning in. And remember, if you're watching these videos, you're part of the class. See you next time, everybody.